Okay, so a quick video on probability. We haven't really done any probability revision together, and in particular the formula that you come across. So I think the two most important formulae you come across are, firstly, if A and B are independent, the way we test that is we work out the probability of the overlap, and these are normally Venn diagram questions, and the pre-release suggests it'll be a Venn diagram, but it could be a tree diagram. And we check that that's actually equal to the separate probability of A multiplied by the probability of B. If it is, then we say those two events are independent. And I'm sure that's going to come up in some way. We're going to do a question in a minute which examines that. If they're not independent, then once A has happened, the probability of B is affected. So we have this notation here, and I'm aware that when I did it before, I sort of tended to use a slash like that, and I look in the exam papers and I'm reminded that they tend to use that notation. But yeah, the probability, if two events are not independent, if one affects the other, the probability of them both happening is the probability of A multiplied by the probability of B given that A has happened. Or of course it could be that it's the probability of B multiplied by the probability of A given that B has happened. And remember, when you are asked a question about two things happening together, like taking two counters out of a bag, the only way we can model that is taking one followed by taking another. And so when we are asked probabilities like this, you may remember I split it into numerator and denominator. So the probability of B given A, well, this is my denominator. So I say, right, what's the probability of A? And then the numerator is, okay, of the probability of A, what part of it is also down to B? So that's how I do the probability of B given A. And of course, that could be written the other way around. The probability of B intersection A, the probability of A intersection B, it's the same thing. And similarly, the probability of A, given that B has happened, well, you say, right, okay, what's the probability of B has happened? And on top, therefore, of that probability of B, what part of it is also down to A? And I think that that formula there, and this sort of common sense, this numerator-denominator approach, is pretty much all you need. I will just show you one thing with my high-tech reveal here. Look at this. How high-tech is that? That the definition of those formulas actually comes from the fact that if this is true, we can rearrange it to say this. And similarly, if this is true, we can rearrange it to say that. So you can sort of derive the two formulas, these two formulas. And remember, A intersection B, B intersection A, it's the same thing. Sorry, I've just realised I've written this the wrong way up. Hang on a minute. The probability of B intersection A is, the probability of A intersection B over the probability of A. I apologise for that. Oh, probability of A. I think I'm just going to give up. Yeah, so the probability of B given A is the probability of A over the probability that A and B both happen. Now, I don't think you need to worry about that if you can remember this common sense approach. Let's have a look at a couple of questions which test that. So again, like I've said before, I'm going to work through these now. So you might choose to pause the video at this point, have a go at these two questions, and then follow the video through with me. I'm also going to give you printed copies of my work solutions, so you may choose to just work through my worked solutions. So if you're going to pause now. Okay, so here is let me just get something to cover, the second one. Here we go. So here is my answer to the first question. So we've got three events here, R, S, and T. And we're firstly asked which are mutually exclusive. Well, that just means no overlap. There's no intersection. So that's got to be R and T. So that means the probability of R intersection T is 0. But there we go. We're then asked which events are independent. So I wrote down the probabilities of R, S, and T. Just R is everything in the R circle, S is everything in the S circle, T is everything in the T circle. And then I wrote down the probability of the three intersections. So R intersection S is 0.05, S intersection T, 0.11, and of course R intersection T is 0, they don't overlap. I then checked if that was the same as the two separate probabilities multiplied together, remembering that independence formula. It wasn't true for S intersection T. The probability of S multiplied by the probability of T doesn't give me that. It's clearly not true for this. If two events are mutually exclusive, it means once one has happened, the other can't happen. So they are very much not independent. But R and S, yes, 0.25 times 0.2 does give you the overlap. So R and S are independent. We're then asked to find R intersection S, and I'm going to use my common sense approach. So I'm going to say, right, this is my denominator. What's the probability of S? 0.2. Of that probability, what part of it is down to R? This bit here. 0.05 over 0.2, it's a quarter. And then we're asked, R given S intersection T dash. So slightly more complicated. So let's look at the denominator first. T dash is T not happening. So it's this, 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 and this. S intersection that, so of this, 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 and this, which part is also in S? So those two. So that's my denominator, 0.09. So that is S and T not happening. Sorry, S happening and T not happening. So that's 0.09. That's my denominator. Of that, of those two probabilities, what part of it is down to R? 0.05. So that's 5/9. Okay, so the second question, this is a little bit more subtle. And I have to say, I got it wrong first time. And you'll be able to see that from my rather low-tech covering here. The mistake I made is that if it's a sunny day, the probability to go to the park is 0.6. I put 0.6 on the overlap. It's not. 0.6 is the probability that she goes to the park given that it's a sunny day. So this is a given that statement. So I need my denominator to be this. So what is the probability of S? Well, I'm told it's 0.45. Of that 0.45, so I know that this is going to be 0.45. We're told that in the question. Of that 0.45, what part of it is down to P? That's what I'm trying to work out here, and that will give me the overlap. So I'm going to do 0.6 times 0.45, and that gives me 0.27. So my overlap is 0.27. If I then do 0.45 take away 0.27, I get the remaining probability of S. Now, if the probability that it's sunny is 0.45, the probability it isn't sunny is 0.55. And we're told that if it isn't sunny, she goes to the park with a probability of 0.2. So that's this. The probability that she goes to the park given that it isn't sunny. And we're told that's 0.2. So similarly, let's work this out. This is my denominator. What's the probability that it isn't sunny? 0.55. That's all of this, isn't it? So this will be what part of that is also down to P, which is this bit not including the intersection. So if I do 0.2 times 0.55, I get 0.11. So the probability of P happening, given that S isn't happening, is the probability of S not happening, 0.55, and on top is the probability which part of that is down to P. So we're then asked, what's the probability that it's sunny, given that she goes to the park? So let's finish my Venn diagram. So I've got 0.18 plus 0.27 plus 0.11 gives me 0.56. So I know that's 0.44 out there. Okay. So what's the probability that she goes to the park? That is 0.38, that's my denominator. Of that probability, what part of it is down to C? 0.27. That's that probability. I think it's really hard to get your head around what this actually means, but actually working it out is really straightforward. Denominator, numerator. Okay.